Hello. Today we are going to study diffusion policy and planning. So these are contents of today, and let's first start with the motivation. So diffusion means like a generative model, right? So we've studied a policy function or imitation learning. Actually, we haven't studied any generative models for reinforcement learning. But these days, with the advancement of generative models, people are trying to introduce generative models for policies. So policy maps observation to an action, that is the policy function that we've learned so far. For many tasks, several different actions are all perfectly valid. So as an example, to avoid an obstacle, let's say there is a car is going in this direction, and then there is an obstacle. An expert might go to left or right. May go left on some demonstration and right on the others. The action distribution is actually multimodal. But there can be many possible actions from the same input states. And we want a policy class expressive enough to represent this complex multimodal action distribution, not just a single average action. So take an example, most of our policy function has a Gaussian action distribution, but it's unimodal, right? So Gaussian distribution is unimodal. Action space is unimodal. Diffusion is also in normal Gaussian distribution, but it's latent space in normal Gaussian distribution, so the action could be multimodal. The diffusion models are powerful generative models that can capture exactly this kind of distribution, which is why we borrow them for policy learning. And let's see the naive behavior cloning problem, an averaging problem. The standard behavior cloning fits a deterministic network by minimizing mean square error to the expert action. This is a typical loss function, right? Just supervised learning, minimize distance between predicted action and the action label. MSE, mean square error, pushes the network towards the mean of targets. If left and right are both correct, the mean is straight ahead, directly into obstacle. That becomes problem, right? A unimodal Gaussian hat has the same problem. It averages mode instead of choosing one. We therefore need a model that represents a full conditional distribution of actions and lets us sample one coherent mode at a time. So there will be two parts. The first one is diffusion policy, which generate the next short sequence of actions by denoising condition on recent observations. Robot manipulation or visual motor control could be examples. And diffusion planning is a little bit different. Generate entire trajectory of states and action at once and steer generation toward a high return. Offline reinforcement learning and planning. We will see detail, but in short, diffusion policy is, we know policy, right? Input is state, output is action. So we just introduce diffusion concept in policy function so that we just simply model distribution of actions. Diffusion model, although it's conditioned on state, it tries to model distribution of actions. But here, diffusion planning, it tries to model distribution of entire trajectory. Trajectory means state and action, which include both state and action. Common thread is replace the hand design policy or planner with a learned conditional generative model that samples behavior. We first do a quick recap of diffusion model since both parts build directly on them. Let's first see diffusion policy. I assume you've learned diffusion models, but let's briefly recap in one picture. So there are two processes, right? The first one is forward and the other is reverse. Forward process, starting from real data, gradually add Gaussian noise over many steps until the sample becomes pure noise. That is the forward process, right? It is not learnable, just to add Gaussian noise to the sample. And reverse process, there is a learning stuff. Train a network to undo one step of noising at a time. So we can start from noise and denoise back into realistic sample, right? The generation is run the learn reverse process. Sample noise, then iteratively denoise to produce a sample from data distribution. So we have some Gaussian distribution, and then sample some noise random z, noise random vector z, and then we denoise network to denoise it to clean sample. That is the reverse process. And that is what is happening in generation process in diffusion model. The only thing the network learns is here, diffusion network, how to predict noise that was added at each step. And for a process, or in other words, noising process, one noising step adds a small amount of Gaussian noise. Changing t steps slowly destroys all structure. A key property is that we can jump into any step t in closed form without simulating every intermediate step with this equation. And equivalently, by the reparameterization trick, we can write the noise sample as a fixed blend of clean data and noise. Like this one. This is forward process. And let's go to reverse process and training. As I said, the reverse process is Gaussian. We learn its mean with the neural network and usually fix its variance. Instead of predicting the mean directly, there are some diffusion models that predict the mean directly, but many of them just simply predict noise that was added. This gives a remarkably simple training loss like this one. So this is, for the early version of diffusion model, this is the only loss function. So this is denoising network, which take noise sample and time step and outputs epsilon. That is the simple training loss, only training loss. In words, take clean sample, add noise at random step, and train the network to recover that noise. That is entire objective. And after training, we can sample by iterative denoising. To generate a sample, start from pure noise and apply the learned denoiser step by step from t equals to large T down to d0. T equals to large T means pure noise. T equals 0 is clean sample. Each step nudges the sample toward data manifold using predicted noise and adds a little fresh noise z for stochasticity. This iterative refinement is what makes diffusion expressive, but it also means sampling needs many network evaluation, which we'll visit later. So unlike VAE or GAN, diffusion model requires iterative sampling. That makes quality of output much better. At the same time, it requires longer sampling time. So diffusion models are widely used in image or video generating models, but we can actually transfer generating image to generative actions. Diffusion models were popularized with images, but nothing in the math is actually image specific. The data x0 can be anything. So the key idea of diffusion policy is to let the data be a sequence of robot actions that make the denoiser conditional on the current observation. So instead of denoise a noisy image into clean image, we denoise the noisy action sequence into clean action sequence given what the robot sees, right? Just simply changing image to action, that's all. The observation is fed it as a condition. It is not itself the noise. So this is just a condition. Like we can design conditional diffusion model, which models distribution of action, and condition is just observation, right? But there's nothing very new or nothing very complicated, just changing image in generative model to action. So let's see the problem set up. At each control step, the policy receives a short history observation, OT, recent camera images or robot states, or LiDAR sensor, anything can be observation. It outputs a sequence or a chunk of future action, large AT, rather than a single action, which keeps the motion temporally consistent. And control runs in reciting horizon style, predict a chunk execute the first few actions, then replan with the newest observation. The policy is therefore a conditional generative model over action sequences, right? So this is condition, this is what we are interested in when modeling distribution. We run the diffusion process on the action sequence, add noise to clean expert chunk, then train the network to predict that noise. So the assumption is that we have clean expert chunk. We have like a teleoperation data that becomes a clean expert chunk. And then remaining things are the same as the image generative model. We add the noise to the clean expert chunk, and then we can train the noising network to predict that noise. That's all. We can follow the exactly same formulation of image generative model, image diffusion models. So the noiser epsilon theta is conditional on observation. So it learns the observation specific action distribution. And here K indexes that the denoising step, and ATK is the action chunk after K steps of noising. Superscript 0 denotes the clean expert chunk. This is just the DDPM loss function, right? DDPM is one of the earliest diffusion model. Now condition on observation T, a clean imitation learning objective with no reward, no environment interaction. So like a DQN or policy gradient, we've learned this kind of reward or environment interaction, right? In PPO, we in our agent interact with the environment, and then we compute predefined reward functions, and then we backpropagate gradient to policy function with PPO. That is the policy gradient, right? But imitation learning, we do not take care about the environment interaction. Let's say we have large amount of prepared data, clean expert chunk, and then we can just try generative modeling instead of any reward computation or any environment interaction. So as I said, exactly same as the image generative model. Only difference is that we are not interested in image distribution, just the action distribution is what we are interested in. After training, sampling actions at runtime is also the same. Given the current observation, start from a noise sample and denoise the action chunk over K equals large K down to 0. Because we sample, each rollout commits to one coherent mode. It goes left or right, never straight into obstacle. Different noise Cs can yield different valid behaviors, which is exactly the multimodality we wanted, right? That is the actual nature of generative model. It can model data distribution in latent space, so that although the latent space is normal Gaussian, unimodal Gaussian distribution, actual sample data can have multimodal distribution, right? And that is actually the motivation of our generative model. There can be many possible actions from the same state, so that we can address such kind of ambiguity, one-to-n problem, by introducing generative concept. The denoiser predict noise over the whole action chunk, and two backbones are common. The first one could be CNN-based one. A 1D temporal unit over action time axis. The observation is injected through film-style feature modulation. And transformer-based one, actions are tokens, and observation conditions them through close attention, often better for high-frequency, sharp action changes. If you have more data, definitely transformer-based one is better. The denoising step index K is encoded. It is sinusoidal embedding and fed into alongside the observation. Crucially, the observation enters only as a condition. We never add noise to it or denoise it. Here, I repeat this. This one is important. This is actually difference between diffusion policy and diffusion planning. We will see this later. Anyway, in diffusion policy, from its name, we can know that it only interested in distribution of actions, and observation is just a condition that we are interested in when modeling distribution. And predict an action sequence, not one step. Generating a chunk keeps actions temporally consistent and reduce jittery, myopic behavior. Reciting horizon execution. Predict a longer horizon for foresight, but execute only the first few actions before replanning, which improves reactivity. So this one is that we're interested in, so our diffusion model. This is our diffusion model. It outputs some actions, right? Some actions. A0, A1, let's say 10. There are 10 time steps. T equals to 10. No, there are 10 actions. So instead of only modeling a single action distribution, right? This one is talking about this one. We model distribution of action sequence for temporal consistency. And the second one says that we have, let's say we have 10 denoised action, but we only actually execute only first few actions, like 3 actions out of 10 actions. And then our agent do something, right? And then we have new observation, and then we we sample again, actions again from the newly updated observation. That is what the second one is saying. And condition don't impede. Feeding the observation as a conditioning input rather than denoising it jointly is simpler and trains more stably. As I said, this one, we feed observation as a conditioning input. We do not perform any diffusion on the observation. And action space diffusion, diffusing in the continuous action space, handles high-dimensional correlated action sequences naturally. And this shows there's a pseudocode algorithm training. Input is demonstration of D of ONA pairs, mostly from teleoperation data. And we repeat below. We sample observation action, and then we sample step K from uniform distribution and noise, and from noisy chunk, we make a noisy chunk, right? This one, it's just a 4 diffusion process, right? And take gradient step, this is loss function, this is forward diffusion, right? Almost exactly same as the image generative models. And inference, one control cycle, we have observation at some time step, and then we sample action from random. This is just a literally normal Gaussian distribution. So the initial sample is just a pure noise. And then we iterative sampling. This is iterative sampling. Iterative sampling. For K goes to large K to 1, we decrease K, right? The noise A superscript K using epsilon theta 4. This is estimated noise, right? Execute first few actions of A0, then repeat new observation, right? So this is iterative sampling, so it takes some time, and then we get some clean action, denoised action, A0. And out of, let's say there are 10 actions in A0, we only execute first few actions, like 3 actions out of 10 actions. Then our agent do something, right? Do something with 3 actions, and then there are updated observation, and then we pass the updated observation to the conditioning information. Then we go back to this stage, right? Go back to this stage and denoise again. Condition on the newly updated observation. This is what is happening in inference time. And let's see why diffusion policy works well. As I said, it's nature of diffusion model, expressive and multimodal. It represents complex conditional action distributions and commits to a single mode per row route, dodging the averaging problem. As I said, there can be from the same state, car. This is obstacle. There can be many possible actions, going left, going right. But simply supervising police function with behavior cloning, our MSE loss function could make our agent converge to the just averaging all possible solutions that will go straight to the obstacle, which may collision. That is not what we want, right? But generative model, it can give us multiple solutions, multiple outputs by sampling, so that we can address such kind of averaging problem. And stable training, unlike GAN or energy-based policies, the simple noise prediction loss has no adversarial minimax and no partition function to estimate. That is the good point of diffusion model. and scales to sequence. Diffusion, an entire action chunk, handles high-dimensional temporally correlate outputs gracefully. And strong conditioning. It naturally consumes rich observations such as raw images, which suits visual motor control. That is why diffusion policy works well. It shares almost the same strength as the image diffusion models, right? And on simulated manipulation benchmark and on real robots, diffusion policies markedly improve success rates over unimodal behavior cloning baselines. They are especially strong on tasks with multimodal demonstrations and long, precise motions, where averaging-based policies tend to fail. They cope well with the idle or paused segments in human demonstration, which often destabilize simpler regression policies. Takeaway is that treating visual motor policy learning as condition action generation is a robust general recipe. And this is the paper, the diffusion policy, presented at RSS 2023. If you're interested in it, you can visit this paper. Of course, there is a limitation. Definitely, it's too slow, actually. For each denoising, we need to do it iteratively. So you suffer from slow inference time. Each action chunk needs many denoising steps, many network evaluations, which is costly for high-frequency control. Maybe we can mitigate this issue with fewer step samples such as DDIM, distillation is consistency models, or flow matching policies that needs only a few or one step. And it's still imitation learning. The policy is bounded by demonstration quality and has no mechanism to exceed the expert or optimize the reward. That is the assumption of diffusion model, generative model. We assume there are large-scale data prepared, but in many cases, including robots, it might not be possible maybe. And out-of-distribution observation can still cause failures since there is no reverse signal pulling the agent back toward good states. This shares the same problem as the behavior cloning, right? Essentially, diffusion model is like a behavior cloning. There is no interaction with environment during the training. So that the diffusion model is trained only on clean samples. But the problem is that the covariate shift problem we learn in behavior cloning, right? Covariate shift problem. When something bad happens, there can be many reasons like a sensor noise or anything. Then agent goes into some weird position. Then catastrophic failure begins. The state becomes weird. Then policy function fails to generalize. Then state goes to more weird position, and then that repeat, so that then we can say nothing about the successful task of our agent, right? If we have huge amount of data, very huge amount of data, then maybe we can address this one. Actually, that is one of strategies that these days diffusion policy models collect as much as data with tailor operation, but when there is a some generation failure, then agent can go into weird position. The covariate shift problem can happen. That is the limitation of diffusion policy. It's not very complicated. If you're familiar with diffusion, then you can see that almost same as the image diffusion models. And diffusion planning is actually a little bit different from diffusion policy. And diffusion planning is actually not only used in this kind of robot manipulation, but also used in video generative models these days. We will see this maybe at the end of this course, but such kind of diffusion planning is actually, or reward-based video generation, video sampling is actually very recent research topic. We'll see this later. Anyway, diffusion planning. So diffusion policy and diffusion planning. A policy answers, what do I do now? Right? The input is state, output is action. So it answers, what do I do now? A planner answers, what is the whole sequences of state and actions that reaches my goal? It's a little bit different, right? So policy, it only tries to model action. And here, sequence of state and action, both state and action. That is the difference. Diffusion planning generates an entire trajectory, pairs of state and action, at once by denoising instead of producing one action chunk per step. Because the full trajectory is generated jointly, the steps are globally consistent and errors do not compound the way that doing step-by-step rollouts. This is naturally suited to offline RL. Learn a generative model of trajectories from fixed dataset, then sample good ones. And one representative paper is Diffusion, presented at ICML 2022. Diffusion treats a trajectory as a single 2D array, state and actions stack over time, and diffuses over this whole array. This is how is, as I said, just pairs of state action. Denoising acts on time and state action dimension jointly, so the model learns which sequences of state and actions are physically plottable. Generation is non-autoregressive. The entire plan appears at once and is refined together rather than one time step after another. Train an ordinary diffusion model on trajectories drawn from an offline dataset using the same noise prediction laws as before. The model learns unconditional distribution over trajectory. So here, this is difference. The diffusion policy, as I said, the observation becomes condition. But here, diffusion planning is unconditional generative model. The model learns unconditional distribution over trajectory, p tau, essentially, what do plausible trajectories look like? At this stage, there is no notion of reward or no goal. The model only captures dynamics and behavior present in the data. All task-specific steering, reach a goal, maximize return, is added later at sampling time, which is what makes the approach flexible. So it tries to diffusion policy. Planning. Let's say random vector z is passed to the model in the inference time, and it outputs the denoising is like a state action as a0, state 1 action, state 2 a2, state t at. But diffusion policy, state 0, state 1, state t are given, and then it outputs action a0, a1, a2, at, right? So diffusion planning is it is an unconditional generative model which denoises the entire sequence, including pairs of state action. But diffusion policy, it is conditional generative model, conditioned on sequence of state and model distribution of action. This is very straightforward, right? The second one, diffusion policy, is straightforward. But diffusion planning, once we design diffusion planning, we can use it in many cases. We will see this later. Like steering, reach a goal, maximize return. Planning as guided sampling. Define the return of trajectory as the usual discounted sum of reward. There can be many reward functions. We can design reward functions in advance, right? To plan bias a denoiser toward high return, goal satisfying trajectory with classifier guidance. This is adaptive general gradient term. So here. And the first term keeps trajectory realistic. The second term forms learn return goal predictor y, pushes them toward high reward. So this one is just a typical gradient we can use for the unconditional generative model. It just tries to make the sampled output plottable, right? But here we have additional one, y, with classifier guidance. Y is classifier. So maybe we want some goal. For example, if we sample some state action, let's say our car avoid this obstacle and reaches to this position, P. And maybe we can design a classifier whether the car, which can classify whether car and obstacle have a collision or car has reached to this position. We can, let's say we have some classifier which can classify such kind of things. Then we can use gradient from this classifier to make our car achieve this goal during this sampling. I mean, this is just unconditional, right? But this is conditional. So we can introduce such kind of conditioning signal during the inference time by using pre-trained classifier Y. The first term, it tries to make the trajectory realistic. It tries to make the sample trajectory in the distribution of our trained generative model. But the second one, we have new classifier, and then it tries to make make our agent achieve a goal. Our car avoid this obstacle while reaching to this position. And some classifier, let's say some classifier can do that. Some classifier can classify whether our car has collision with this obstacle and our car reaches to the position. Then we can use gradient of this classifier for the sampling, in the sampling stage. That is called guided sampling, right? We can also condition it by inpainting. Fix known entries of trajectory, the start state and a goal state, and let the denoising fill in the rest. Let's see the algorithm. Given start state as 0, optionally a goal, train return models J, sample trajectory tau, this one. Let's start with the pure noise, fix known entries. This is what we know. And for the iterative sampling, denoise one step to our realistic tau. This is unconditional, so that we can just pass this tau k to our denoiser. Then we can denoise it one step and add guidance gradient here to our high return. We can introduce such kind of guidance during the inference with some which maximize the high return, and reapply fixed entries and execute first action of tau 0, replan from new state. Repeat this again. Right? The important thing is that we introduce additional gradient from J tau to maximize high return, where return can be defined for your design. It depends on your design choice. So why we do this? Because diffusion policy, it is trained to simply output actions based on states. But diffusion planning, there's no condition, right? So that when we need to use this kind of diffusion planning, we need to achieve some goals. But as it is unconditional generative model, we cannot enforce our model to satisfy some conditions because it's unconditional generative model. So alternatively, instead of passing condition as an input like diffusion policy, we introduce such kind of gradient-based conditioning in the inference time for diffusion planning. Decision diffuser is another paper presented in iClear 2023. Classifier guidance using classifier Y. Here, Y is a separate model of the return gradient, and this gradient can be noisy and hard to train offline data. The decision diffuser instead uses classifier-free guidance. A single conditional diffusion model is steered by a condition variable directly with no extra gradient model. So it tries to get rid of classifier Y. Then that is called classifier-free guidance. Classifier-free guidance is actually very widely used in diffusion models. It reframes diffusion making as conditional generative modeling, generate a trajectory that achieves this desired outcome. This makes conditioning on returns, goals, constraint or skills clear and modular. Let's see some example. Train one network that can run with the condition C, a target return, and without. Sampling combine two noise prediction. This one C. So this one is estimated noise, estimated noise. So we make a boost in the direction of condition C, right? Let's say W is like a positive number, like a 2.0. And this epsilon, this noise estimated epsilon, the condition is empty set, right? It is not aware of any condition. But here, C is given, and here empty set. So that we push our sampling in the direction of considering C with the weight of 2.0, right? That is the classifier-free guidance. Here we do not have any classifier, we do not have any pre-trained classifier, but we introduce this classifier-free guidance during the inference time, during the sampling of state action pairs in the direction of considering the condition with weight 2.0. The weight W controls how strongly generation is pushed toward the condition. Larger W means trajectory that more aggressively satisfies C. No separate classifier or return gradient model is required. The same denoiser provides both terms. So these days, actually, most of people just use classifier-free guidance. I mean, because preparing classifier is not very trivial. We need some data to train classifier, and the gradient could be noisy. That actually these days, almost all people just use classifier-free guidance instead of introducing classifier for the diffusion planning. And decision diffuser diffuses over the sequence of states only, which is smoother and easy to model than noise action sequences. So this is another difference. Only state. So the diffuser, the previous paper, it models distribution of state action together, right? But here, decision diffuser, it diffuses over the sequence of states without action. And actions are then recovered from consequent generated states with the separately trained inverse dynamic models. So planning produces a state path, only state without action. And phi converts each state transition into the actions that realizes it. Splitting what states to visit from how to move between them makes both sub-problems easier to learn. So that is the difference between diffuser and decision diffuser. It only models states without actions. And of course, we need action to execute our robot to do that, so that we recover actions from separately trained inverse dynamics model. Decision diffusion returns a condition on a desired high return so that model generates trajectory that achieves it. Generative take on return condition reinforcement learning. Constraint is the condition on satisfying a constraint stay in a region, and the sampler produces feasible trajectories. Skills are conditioned on discrete skill or behavior labeled to compose and reuse behaviors. All of these reuse the same train model, only the conditioning variable changes the sampling time. That shows the flexibility of decision diffuser, right? So let's say we have noise, and then model, and then state. Then depending on your condition, for example, if you want your car reach to this direction or this direction, depending on your goal in the inference time, you can introduce just a different classifier-free guidance without retraining diffusion models. That shows flexibility of decision diffuser, right? We have state, then we can introduce classifier-free guidance with the noise states, depending on your goals, right? That we do not have to retrain our diffusion model again to simply reuse it, a single train diffusion model, and then we can reuse it for any condition. That makes our system very flexible, right? So here, this shows the algorithm of decision diffuser. Train state diffusion model. Here, state diffusion, as I said, it's only interested in state. Epsilon theta, randomly dropping C. Dropping C, this is for classifier-free guidance. Dropping C teaches both conditional and unconditional prediction. Train inverse dynamics on dataset transition, and then choose condition C. That depends, as I said, that depends on your choice. In some cases, you want your condition C or different C, it depending on your cases. Sample state path by denoising with classifier free guidance, weight W. For each step, AT is recover with the inverse dynamics model, execute AT, replan. That is algorithm of decision diffuser. So let's see the difference between diffuser and decision diffuser. Diffuser, classifier guidance, but the decision diffuser, classifier free guidance, right? So we no longer need to train classifier. What is diffused? Diffuser, state and action jointly, but only state. Getting action, because it models action, we can just get directly from sample trajectory, but action, inverse dynamics from states. Extra model, separate return gradient, but no, because we do not need any classifier. Conditioning goal, return via guidelines or in painting, return constraint or scale. And what is the difference between diffusion policy and diffusion planning? Diffusion policy, short action chunk, but full trajectory, pairs of state action. Recent observation, return goal, constraint. Horizon short, reactive, long global. Uses reward, no, but it kind of yes, right? It is interesting. So during the inference time, after training, during the inference time, during the sampling time, we can introduce some reward, and then, so based on interaction with the environment, we can steer, we can make our agent achieve that reward during the inference time. That is the interesting point of diffusion planning, right? But here, no. Diffusion policy, state is given and in output action, then we do nothing. Just simply we need to follow the sampled action. But here, diffusion planning, we have some condition, and then we know we want some goal during the inference time. We can update some goal, and then we can steer our diffusion planning or achieve that goal in the inference time. So we can have interaction. We can consider some interaction with the environment during the inference time for diffusion planning, right? That is some interesting point. And diffusion policy uses no reward at all. It is the behavior cloning, so performance is capped by the demonstration. Diffusion planning brings reward back in, but not through the policy gradient update. Reward enters as guidance or as a conditioning variable at sampling time. This sidesteps unstable bootstrapping and works well on fixed offline dataset, but it cannot collect new data to surpass what the dataset supports. A growing line of work fine-tunes diffusion policies with reinforcement learning, treat a denoising chain as a sequence of action to optimize for reward. That is also consistent with recent trend of video generative models. After training video generative models with diffusion loss function, people introduce some RL stuff like DPO or GRPO. We will see this later at the maybe last of this lecture. That is also consistent with the recent trend of video generative model. Post-train video generative model or policy function, diffusion policy with reinforcement learning. Practical considerations, denoising steps, latency. More steps gives higher quality but slower control. Few step samplers and distillation trade a little quality for speed. Action planning horizon. Longer horizon improve foresight and consistency, but are hard to model and slower to sample. Guidance weight. Too small ignores the reward goal. Too large produce unrealistic off-manifold trajectory. It must be tuned. Data quality. All of these methods are offline, so the convergence of quality and the dataset largely determine the ceiling on performance. And let's summarize. Diffusion models give us expressive multimodal conditional distribution, which fixes the averaging problem of naive behavior cloning. Diffusion policy generates short observation condition action chunk, a strong stable recipe for visual motor control. Diffusion planning generates the whole trajectory and steers them with the return guidance. Diffuser or classifier free condition decision diffuser. Reward enters through sampling time guidance conditioning rather than policy gradient, which fits offline RL but is bounded by the dataset. Open challenge across all methods, making iterative denoising fast enough for real-time, high-frequency control.